Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of validating a binary search tree, which I'm going to be referring to as a BST from here on out. Now, I will make a quick aside before we start the video, which is that if you don't feel comfortable with BSTs or you're unfamiliar with them, I urge you to look at the question called BST construction in the BST category right here on algoexpert.io. In that question and in the video that accompanies the question, we cover everything about BSTs, how to implement them, how to construct them, what their sort of main methods and properties are. So definitely check that video and question out. Now, without further ado, let's dive into validating a BST. So this question wants you to write a function that's going to take in a data structure that looks like a binary tree, meaning the data structure consists of nodes where each node has a value and then optionally a left node and a right node. These left and right nodes can just be none values or null values, or they can be actual nodes, other nodes. And the question wants you to determine whether or not this data structure is actually a BST. In other words, does it satisfy the special BST property? Now, there are a few different variations of the definition of a BST. The one that we'll be using, or the BST property, the one that we'll be using here is that every node in a binary tree, in order for a binary tree to satisfy the BST property, every node in it has to have a value that is strictly greater than all the values of its left nodes, and it has to have a value that is greater than or equal to all the values of its right nodes. And then also, its left node and its right node must be BSTs themselves. So, how do we solve this question? Well, in front of me, I've got an example BST, or binary tree rather. It so happens that this BST does satisfy this binary tree does satisfy the BST property. So we can write true here. We want to return true for this example. So we've got our binary tree, and we want to determine if it satisfies the BST property. One way that we can solve this, which is probably my favorite way, involves a sort of divide and conquer approach where we're actually, we're going to start at the root node and we're going to validate all the subtrees until we can validate our final tree. So we're going to kind of go down, we start at 10, we're going to validate the left and the right tree, or perhaps invalidate them. Then for each of those, we're going to validate their left and right trees. And for each of those, we're going to validate their left and right trees, and so on and so forth. Now, the important property here that we have to realize is that every node in a binary tree, or in a BST rather, has a minimum value and a maximum value. And so to explain what I mean by that, let's look at an example, okay? Let's look at this 5, the second 5 that we have in this BST. So I'm actually going to circle it in purple so that we don't forget which 5 we're looking at. This 5 has a minimum value and a maximum value. Perhaps I should rephrase this and say this node here that has a value of 5 has a minimum possible value and a maximum possible value. The minimum value that it has is 5. And why is it 5? Because this node here is the right child of this node, which is also a 5. So I'm going to circle this 5 here. This purple circle node is the right child of this green circle node. In other words, the value of this node has to be greater than or equal to the value of this node. Therefore, its minimum value is going to be 5. Okay? Now, similarly, this node, if we go up its sort of ancestor tree, we have the 5 as its direct parent, and then we have another parent here, which is the 10. And so because our purple 5 here is to the left of 10, it's in the left subtree of the 10 node, the brown or orange circle, that means that this node has to be less than, strictly less than, this node. Or rather, the value of this node has to be strictly less than the value of this node. So the sort of maximum value of our purple node here has to be less than 10. So we can say that, the purple node, the value of the purple node has to be strictly less than 10, and it has to be greater than or equal to 5. It must be between these two values. And we can actually find these two values that wrap a node's value for every single node. So, for instance, if we look at now the 13 here, okay, let me underline this 13 in white. If we look at this 13 is the immediate left child of 15, which means that, let's write it in white. So, node dot value has to be strictly less than 15, because 15 is its direct parent node, and 13 is to the left of 15. And then similarly, if we go up the tree, we see that 13 is to the right of 10. It's in the right subtree of this 10 node. Therefore, it must be greater than or equal to 10. So here we can add greater than or equal to 10. And so now we have that the value of our white node, which is this 13 that we underlined in white here, has to be greater than 10 or equal to 10. And it has to be less than 15. So by wrapping these nodes between two values, we can actually kind of traverse the tree and validate our nodes by checking if they're wrapped between their min value and their max value. But now you might be asking, okay, how do we come up with the minimum value and the max value in our algorithm? It seems like it would be really hard and probably inefficient to have to go back and find parent nodes. And so what we can actually do is we can probably create some kind of helper method that's going to take in additional arguments, a min value and a max value, and we're going to pass down those values as we traverse the tree. So what's going to end up happening is we're going to start at this root node, this 10 node here, the node that has the value 10, and we're going to initialize the minimum value and the maximum value to be infinity and minus infinity. So if we initialize, because at the beginning we can kind of say, the root node has to have a value that's between negative infinity and positive infinity. And so then, for each node, we check, does the value of our node fit between our minimum value and our maximum value? And at the beginning, 10, or whatever value we have here in this root node, is always going to be greater than negative infinity and less than plus infinity, right? But so, because any sort of single node is actually a valid BST. But so once we determine that our current node's value is in between its minimum value and its maximum value, we can call our function on the left subtree and the right subtree, and we can pass in a different minimum value and a different maximum value. So what we can do is we can say, when we call our method on the left subtree of a node, we're going to change the maximum value to be the value of our current node. Because if we look at this 5 here, the 5 that we have in green, right? The maximum value of the 5 in green is no longer infinity, it's 10. Because 5 has to be strictly less than 10. So when we were at the 10 node here, and we call the function on our left subtree, we can change the maximum value to be the current value of our node, which is 10. And so then when we get to this 5 here, the green 5, we want to check that 5 is greater than negative infinity and less than 10. And then similarly, when we call the function on a right subtree, we update the minimum value. So here, when we call the function on the right subtree of our green node, which is going to be this purple node, we're going to update the minimum value to be the value of our current node, which is the green node, which is going to be 5. So for this purple node, we're going to have 5 as the minimum value and 10 as the maximum value. Whereas for the green node, let's write it here, we're going to have node dot value is less than, let me write it in white, less than 10, but it's greater than or equal to a negative infinity. Okay? Because that was the minimum value that we passed on from the top. And so that's how we can kind of narrow down the minimum value and the maximum value for each node. And that's how we can sort of, in a divide and conquer approach, validate every subtree to then validate our given subtree that starts at the root node. And I guess I should point out that whenever we reach a none value, in other words, a leaf, a node that doesn't have any child nodes and that doesn't have a value. So, for instance, at the end of this 1 here, we'd have 2 none value nodes. And whenever we reach a none value, we can just say, okay, this is a valid BST, and we can kind of recursively climb up our tree. So before we dive into the code walkthrough, which I think will make a lot of things clearer, let's look at the time and space complexities of this algorithm. In terms of time complexity, it's pretty straightforward. We're going to have a time complexity of O of n, where n is the number of nodes in the BST, or in the tree rather. Why is it O of n? Well, we're traversing every single node in the tree, right? Like, we cannot skip a node. So because we're traversing every node once, the time complexity is O of n. And I guess it's worth mentioning that every sort of computation that we do on a given node is a constant time computation. Like checking that the node's value is between the minimum value and the maximum value that it has, that's a constant time operation. So we've got a time complexity of O of n. Now, what about the space complexity? So the space complexity is slightly trickier. We are not using any additional space in terms of variables that we're storing or pointers that we're storing or things like that. What we are doing, though, is we're using space on the call stack, because we're calling the validate BST function on all of our subtrees, and it's only once these functions resolve that we can kind of go back up and clear space on the call stack. Because, again, if this is unclear, when we call the validate BST function on our root node here, the 10 node, the orange node, we check that the value is between the minimum value and the maximum value, and then we call the validate BST function on the left subtree and on the right subtree. And until these two functions kind of resolve and we hit their return value, the call of validate BST on this root node is going to be on the call stack. And then similarly for the calls on the left and right subtrees, we're going to then call validate BST on their children nodes. And so these calls are also going to be on the call stack. And so the space complexity ends up being O of D, where D is the depth of the tree. So why, first of all, what is the depth of the tree and why is it O of D? Well, the depth of the tree is the length of the longest branch in the tree. So in this case, it would be probably to the left here. You know, we've got 4 nodes back to back, 10, 5, 2, and 1. Similarly, on the right here, we've got 10, 15, 13, 14. So that's actually also a depth of 4 here. But the idea is that this is the longest branch, and so this is the biggest amount of space on the call stack that we're ever going to be using at once. Because, you know, there's going to be a point where we call validate BST on the 10 node, then we call validate BST on the 5 node, then on the 2 node, then on the 1 node, and probably then actually on the none nodes, and only then do we go back up. And so that's going to be the sort of the largest amount of space that we ever use on the call stack. And so the space complexity can be expressed as O of D, where D is the depth of the tree. I guess it is worth pointing out that if the tree only had one branch, let's imagine our tree only had one branch, then in that case, O of D would be equal to O of N, because every node in the tree would be in that one branch, and so the depth of the tree would be the same as O of N, as its number of nodes. So with that being said, let's dive into the code walkthrough. All right, so we've got our validate BST function defined. It takes in a tree, and the first thing we're going to want to do is write a helper function, because as I mentioned before in the conceptual overview, the root node is going to want to have a minimum value and a maximum value of negative infinity and infinity. And more importantly, whenever we call validate BST on every subtree after the root node, we're going to want to pass in a minimum value and a maximum value. But here, our validate BST function only takes in a tree. So what we can do is we can say return validate BST helper. We're going to have a helper function. And this helper function is going to take in a tree, as well as a minimum value and a maximum value, which we're going to initialize at the beginning as negative infinity and maximum or positive infinity. And so, of course, depending on your language, you might want to just use, whatever the maximum integer value is and minimum integer value is in your language. Now, the helper function, as we just mentioned, is going to take in a tree, a min value, and a max value. And the first thing we're going to want to do here in the helper function is check if we are at a leaf node, meaning at the very bottom of a branch in a sort of none value. So if the tree is none, then we can just return true, because we've hit the bottom of the tree, and any node that has the none value is theoretically a valid BST. Now, after that, if we are at an actual node that isn't just the none value, we can say we want to check that the node's value has, or rather is, between the minimum value and between the maximum value. So we want to check that we can say if the tree's value is less than the minimum value, or the tree's value is greater than or equal to the maximum value, then we return false. So let's pause for a second here and see what we're doing. Remember, every node has a minimum value and a maximum value. The minimum value, it has to be greater than or equal to that, according to our BST property definition. The maximum value, it just has to be less than the maximum value. It has to be strictly less than the maximum value. So, in order for those two sort of conditions to be broken, the tree value has to be either strictly less than the minimum value or greater than or equal to the max value. And so if if one of these two conditions is broken, then we return false. And then if we're potentially, if our node is like valid up to this point, then we want to check that its left subtree is valid as well as its right subtree. So we can say left is valid is going to be equal to validate BST helper, that's where we call the function, on the left subtree, passing in the minimum value, and passing in the current tree's value. Because remember, we're looking at a left subtree. So we know that the node immediately to the left has to be strictly less than our current tree's value. In other words, the node immediately to the left of us has to have a max value of our current tree's value. Okay? And the minimum value is the same that we have in this current call of the function. And then we can say, just return left is valid. So return the fact that the left subtree is valid. And also we want to see that the right subtree is valid. So and validate BST helper on the right subtree. Except this time we pass in the tree's value as the minimum value. Because why? If we're going to the right, we know that the node immediately to the right has to be greater than or equal to our current value. So its minimum value is our current value. So that's why we pass in our current value as the minimum value. And the max value is the same one that is in the current call of the function. And that's it. Basically, we will either end up at the bottom of a branch, in which case we return true and we kind of start climbing back up through our tree and clearing up frames on the call stack, or we hit this case where the value of our current node is not in between the minimum value and the maximum value, and we return false in that case. And then we return these two. We return that the left subtree is valid and that the right subtree is valid. So this function runs in O of n time, as we mentioned, because you have to traverse every single node. And it runs in O of d space, where d is the depth of the tree, because at most we will have d calls on the, or d frames on the call stack being used up. Because, we're going to be calling validate BST helper and using up frames on the call stack all the way till we reach a branch or a leaf, the bottom node at a branch. And then we start climbing back up and clearing frames on the call stack. And so the longest branch has length d, where d is the depth of the BST, or of the tree. So that's it for this video. I hope it was helpful, and I'll see you in the next one.